Good afternoon or evening, AP Calculus students. This is my Unit 5 review packet now. So after this one, we just have two more left. And this is largely on, the title is Contextual Applications of Derivatives. And really, we're dealing with how do derivatives go into like in real life rates, like certain rates, for example, specific ones are like velocity and acceleration and stuff like that. So that's what this packet is about. All right. The first topic that we dealt with are related rates. And let me discuss specifically what related rates are. What are related rates? Well, just like how optimization problems are like first derivative test problems, but in like word problem form, well, related rates are basically implicit differentiation problems in word problem form. Right? So same sort of thing. It's taking derivative knowledge we already know, like we know how to do product quotient rule, all these sort of rules, but putting it into a real life sort of application. That is all that is going on here. So let's take a look at the steps for related rates. So step one is just like optimization, we're going to draw a picture. All right, draw a picture. Well, when I look at this problem here, we already have a picture, so we are good. Step two, we're going to do a know/don't know and don't know chart. All right, so let's actually do that here. What do I know? Okay, they gave me a few things that I know already, which is great. So I know that dz over dt is equal to 1. So actually, I'm going to write no here. No. I know dz over dt is equal to 1. I know weirdly dx over dt is equal to 3 dy over dt. Seems a little odd that I know that, but that's fine. I know x is equal to 4, and I know y is equal to 3. What do I not know? I don't know dx over dt. All right, I may try to add stuff to here, but for the time being, this is everything that I know, right? Okay, because that's all they gave us in the problem. Right. You'll notice we may be able to figure out a few things. For example, if I know x is 4 and y is 3, hint, we should be able to figure out z, right? But since they didn't give us that in the problem, I'm going to only figure that out when we get there. All right, let's go on to our step 3. Step 3. Identify equation that relates all the variables. Okay, so what equation do we think we're going to deal with here? Well, we have a clear triangle, y, x, and z, right? All right, so what equation will we deal with in terms of a triangle? There's only two types of equations. Maybe it's the area equation. Area equals 1/2 base height. But they don't really ask about any side of, or any area of a triangle here. In fact, they say the sides of a rectangle, right? X, Y. But luckily, they gave us this picture. I can clearly see we're really dealing with a triangle, right? So the equation we're much more likely to deal with is Pythagorean theorem. Basically, a squared plus b squared equals c squared, or in this case, x squared plus y squared is equal to z squared, right? That's the equation that relates my x, y, and z, the stuff that's labeled in my picture. Cool. Step 4, we're going to implicit differentiation. That's my step 4. Basically, this gives me a rate equation with respect to time t. All right, so how do I do implicit differentiation? Well, if you remember, we already practiced this, but d over dt of both sides of my equation. So d over dt of x squared plus y squared, d over dt of z squared. Let's do my derivative. Derivative of x squared is 2x. But then this t and x do not match. Remember, just like when the y and the x don't match, when there's a y term, I multiply by dy dx. In this case, I'm going to multiply by dx over dt. Cool. Next one, y squared. I first take the derivative normally. Then I have to multiply by dy over dt. All right, that's equal to d over dt of z squared. Well, derivative, first I take it normally, so 2z. Then, since the variables are not the same, t and z, I have to multiply by dz over dt. All right, so this here, I'm gonna label step 2. This is an important step. So I want to star this. I'll put an exclamation point. And step 4 is also a really important step. We got to know how to do these because step 4 is my implicit differentiation. That's just knowing how to do a derivative rule. Cool. I have my step 4. Now step 5 is literally plug it in. Plug in values we know to figure out what we don't know, right? So now I'm just going to plug stuff into my function, into my equation. All right, 2x. Do I know what x is? I should. From my equation, from my no chart, x is equal to 4. 2 times 4 times dx over dt. Well, I don't know dx over dt. That's okay, because that is what I'm looking for. So dx over dt, I don't know. That's fine. 2y, y is 3. dy over dt, I actually don't know what that is necessarily, but I know dx over dt is equal to 3 dy over dt, right? So this was from my chart. Dx over dt is equal to 3 dy over dt. So in a way, I actually do know what dy over dt is. Dy over dt is equal to dx over dt divided by 3. Right? If I were to solve for dy over dt, it's equal to dx over dt divided by 3. And that's probably useful because I'm trying to solve for dx over dt. So me getting rid of dy over dt, so I can find it in terms of dx over dt, that's probably valuable. So I'm actually going to paste it there. Instead of dy over dt, I have dx over dt divided by 3 because they are equal to each other. All right, finally, 2z. I said I don't know what z is, but I could probably figure it out. I could probably figure out z. And then finally, dz over dt. They tell us that is 1. So I do know dz over dt. That is just 1. So I'll put 1 in there. So I can almost solve for dx over dt, except I need to know what z is equal to. Well, what is z equal to? I can figure that out through Pythagorean theorem, right? I know 3 squared plus 4 squared should be equal to z squared. And some of you might have this pattern memorized, but if not, you can just solve it. 3 squared is 9. 4 squared is 16. That's equal to z squared. 9 plus 16 is 25. So 25 is equal to z squared. That means z is equal to 5. Z is equal to 5. Hopefully you can see the math there. So I'm going to put 5 there. Okay, cool. So I have everything plugged in except for dx over dt, which is fine because that is what I'm looking for. So now we just have to solve for it. So plug in the values we know. I did this to figure out what we don't know. We're about to do this. Right, that's great. Let's just plug everything in, which I did, and let's just simplify. So 8 dx over dt plus 2 times 3 times dx over dt divided by 3. These 3's cancel out, so it's just 2 dx over dt is equal to 10. 8 dx over dt plus 2 dx over dt, that's just 10 dx over dt is equal to 10. That means dx over dt is equal to 1. So my answer, what is the value of dx over dt? The answer is B, 1. All right, hopefully that makes sense. Okay, we're going to move on to the next question, which is still a related rates problem. So I'm going to just erase some of this work, but I'm going to keep the steps because remember, it is the same steps. All right, the radius of a circle is increasing at a constant rate of 0.2 meters per second. What is the rate of increase in the area of the circle at the instance when the circumference of the circle is 20 pi meters? Okay, first step, draw a picture. I can do that here actually because they don't give us a picture. I'm just drawing a circle. This might be useful to have. Okay, so not the best circle, but all right. The radius of a circle increasing at constant rate of 0.2 meters per second. What is the rate when the circumference of the circle is 20 pi meters? Okay, the circumference is 20 pi. I guess I'll write that. I don't know my radius, but I do know the rate of change of the radius is 0.2. Okay, cool. My picture is not great, but let's just say I have this. Step 2, my know and don't know chart. What do I know? I know the radius of the circle is increasing at a constant rate of 0.2 meters per second. I put an exclamation point on this step because it's important for us to know how to write this. So it would be a mistake for me to say my r is equal to 0.2 because it does not say my radius is 0.2. It says the rate of change of my radius is 0.2. So really, it's dr over dt is equal to 0.2, and I'll put meters per second. Right? That's what I do know. Okay, 0.2. Okay. What else do I know? I know the circumference is 20 pi meters. Circumference is equal to 20 pi meters. Cool. Okay. What do I not know? What am I trying to find? What is the rate of increase of the area? Okay, so another test. Make sure you don't just think I'm trying to find area. I'm not. I'm trying to find the rate of change of the area. So dA over dt is equal to what? All right, so I have my know and don't know chart. Identify the equation that relates all the variables. All right, so this one's a little tricky, and I'll show you how I would think about this. Equation that relates all the variables. So I'm dealing with a circle. Normally, I've just jumped straight to area is equal to pi r squared, right? Area is equal to pi r squared. And that makes sense because I'm looking for the rate of change of the area, I'm given the radius, etc. But also, I have circumference here. So I'm going to just, to be safe, I'm going to write down two of my equations. My area is equal to pi r squared, but also my circumference, the equation for that is 2 pi r. So I have two equations. Hopefully you have those memorized or somewhere. You could figure that out. All right. Step 4, I'm going to do implicit differentiation. So I'm going to take d over dt of both sides. So let's do that. Derivative of a, derivative of pi r squared. All right. Derivative of a. Well, derivative of a is just 1, right? I take the derivative normally. But then I need to multiply by dA over dt. Excellent. All right. Right side. First, I take the derivative normally, right? So 2 pi r. But then my r and t do not match, so I need to multiply by dr divided by dt. Right? I have to multiply by that because it's implicit differentiation. That's just how you do implicit differentiation. So I'm going to simplify this a little bit. And notice I'm trying to find dA over dt. My dA over dt is right here. So I'm sort of good. I have what I'm trying to find for. I just need to be able to fill out this right side. So let's leave this c equals 2 pi r. Just leave it there for right now in case we need it. Since I already found the variable I'm trying to look for here, the dA over dt, I'm just going to leave it there because I don't need to do implicit for this yet unless I absolutely have to. Okay, step 5, let's plug in the values we know to figure out what we don't know. All right, so I'm trying to figure out d over dt, so I don't know that. 2 pi r, do I know what my radius is? I actually don't. According to my chart, my no chart, I don't know what that is. Okay, dr over dt, do I know what that is? According to my chart, I do know what that is. That is 0.2. All right. So let's look at this again. The only thing that is holding me back is this r. Once I figure out r, I can solve for dA over dt. So what is my radius r? Let's go back. Is there anything I can use? Well, you'll notice I never used this c is equal to 20 pi. Just never used it. Well, if I were to use it, c is equal to 20 pi. That means I can change the c to 20 pi. Notice I can figure out what my r is equal to. If 20 pi is equal to 2 pi r, this r must be equal to 10. So basically, another thing that I do know, since my circumference is 20 pi, I actually can figure out my radius and figure out that my radius is equal to 10. This allows me to actually solve for my final answer because my radius is 10. So 2 pi times 10 times 0.2. Well, that's going to be 2 pi times 2, which is equal to 4 pi. Right? So my rate of change in my area is 4 pi. So my answer is going to be C. Hopefully that makes sense. All right. Next problem. All right. Next problem is a related rates problem, but it's a little bit weird. So let's just still try to fit it in the steps that we know. Step 1, draw a picture. Can I draw a picture for this? Not really, right? I can't really draw a picture for that. Step 2. Step 2 is know and don't know chart. Let's see. What do I know? I know x is equal to 8. I know the rate at which the cube root of x is increasing is 1 over k times the rate at which x is increasing. Okay, that's weird to write. So, because these weren't given functions, let's call this function y and call this function z. So, the rate at which x is increasing, dy over dx, is equal to 1 over k times the rate at which z is increasing. So dz over dt. So like I was saying, this isn't a normal related, I mean, it is like a related rates problem, but if we do our traditional steps, it can be a little confusing, but that's okay. What is the value of k? So I don't know what k is. All right, step 3, let's find an equation that relates all my variables. Well, we're not actually given that, but we are sort of given the rate at which cube root of x is increasing is 1 over k times the rate at which x is increasing. I can find these. So I can find my dy over dx, right? If y is equal to cube root of x, so cube root of x, that is the same as x to the 1/3. That means I can find my dy over dx. That's simply my derivative, right? So it's 1/3 x to the negative 2/3. I just did a power rule. All right, same thing with here. To find dz over dt, if z is equal to x, that means dz over dt is equal to 1, right? Because derivative of x is 1. So what are they really saying here? The equation that relates all my variables is this equation. Dy over dx is equal to 1 over k times dz over dt. Dy over dx, that's my derivative. It's really 1/3 x to the negative 2/3. That's the rate at which x is increasing. So actually, I'm going to write that here. The rate at which x is increasing is 1 over 3 x to the negative 2 over 3, right, is equal to 1 over k. So it's 1 over k times the rate at which x is increasing. So times, well, the rate at which x is increasing, that's the derivative of x times 1. Right? dz over dt, we said here, is literally 1. Okay, what is the value of k? Well, I just need to solve this equation. Right? Step 4, plug in values and solve. All right, so let's plug in my values and solve. Actually, we sort of skip step 4 is find the derivative. We already did that here. We found the derivative. So this is sort of my step 5, actually. Plug in values and solve. So I take my equation. 1 over k times 1, that's just 1 over k. So really, I'm just plugging in my value for x. X is going to be 8. They told us x is 8. All right. So x is 8. So I just need to simplify this and solve for k. All right. Well, when it's to the negative 2/3, I can move that to the bottom, times 8 to the positive 2/3. Okay, 8 to the positive 2/3, that is the cube root of 8 squared, that's just another way to write this as a changing my fractional exponent back into root form. Okay, cube root of 8 squared, that's the same thing as cube root of 64. Cool, I'm just showing this step by step. Cube root of 64 is actually 4. So 1 over 3 times 4. That means 1 over 12 is equal to 1 over k. You can see here that means k is equal to 12. So my answer choice is E, k is equal to 12. All right, hopefully that makes sense. Next question. The radius of a sphere is increasing at a rate of 0.3 inches per second at the instant when the surface area becomes 100 pi square inches. What is the rate of increase in cubic inches per second in the volume V? All right, let's do step 1, draw a picture. And this one looks like it's another one of those that's valuable to draw a picture because we're talking about an actual object here. So a sphere looks like a circle, but pretend it's a sphere. The radius of the sphere is increasing at a rate of 0.3 inches per second. So my radius is right here, and my radius is getting bigger. Make sure I'm not going to label my radius as 0.3 because it's not 0.3. At the instance when the surface area becomes 100 pi square inches. Okay, so if I were to write my surface area is 100 pi. What is the rate of increase in cubic inches per second in the volume V? All right, draw a picture. Step 2, I drew everything that I sort of can. Let's draw my know and don't know chart. All right, what do I know? Well, I know that I drew on my picture, surface area is equal to 100 pi. That's great. What else? I know the radius of my sphere is not 0.3, but it's increasing at a rate of 0.3. So really, dr over dt is equal to 0.3. Okay, let's see. Do I know anything else? Not really. I mean, I know these equations. They gave me this equation, so I guess that's sort of useful. I'm going to write down my equations. 4 pi r squared v equals 4/3 pi r cubed. All right, what do I not know? Okay, well, I don't know. What am I trying to find? What is the rate of increase in cubic inches per second in the volume V? So I'm trying to find the rate of change of my volume. So I'm trying to find dV over dt. That's ultimately what I'm trying to find. I'm not trying to just find the volume. I'm trying to find the rate of change of the volume, so dV over dt. All right, step 3. I'm going to identify an equation that relates all the variables. Identify an equation that relates all the variables. All right, well, I have 2 equations written here, so it's very high chance it's going to be one of these. I have surface area, dr over dt, dv over dt. Okay, it might be both these equations, but considering I'm looking for dv over dt, the equation that relates my most important variables is going to be this one. But I'll keep this one here as well because that might be useful. Right, so that's one that relates all my variables. Step 4 is going to be implicit differentiation, because these are all related to time. So I'm going to take d over dt of both sides. d of v, d over dt of 4/3 pi r squared. Derivative of volume is 1, but then I need to multiply by dv over dt. Cool. Derivative of this right side, derivative of 4/3 pi r cubed. I first do a power rule, so it's going to be 4 pi r squared. Right, so that's just a power rule. But then my variable is r, and it's with respect to t, so I need to multiply by dr over dt. That's my implicit differentiation step. Cool. Let me simplify this a little bit. I can get rid of this 1. All right. Step 5. Plug in known values and solve for what you don't know. All right, let's just plug in stuff now, right? So dv over dt, I don't know this. That's fine because I'm not supposed to. 4 pi r squared. What is my r? Do they give me my r? They don't actually give me my r. That's annoying. So I don't know my r. Do I know d over dt? I do. That is 0.3. This is actually super similar to one of the problems we just did. I just need to figure out my r. That's the one thing that's stopping me from solving for my answer. Well, what is my radius? Well, what have we not used? Again, I haven't used this equation. I also have not used that s is equal to 100 pi. Well, think about it this way. If s is 100 pi, that means this s here I can replace with 100 pi. That means I can solve for r here. And if you were to solve for r, you should get that r is equal to 5. Right? R is equal to 5. So you can write this down yourself. I would like for you to write this down yourself. Solve for the r here. You should get r is equal to 5. So actually, an additional thing you do know, it's just hidden, is that your radius is equal to 5. So radius is 5 here. Cool. Let's just simplify this. So 4 times 5 squared, so that's 4 times 25. Times 0.3. So that is 100 pi times 0.3. So that means dv over dt is equal to 30 pi. All right, so my answer choice is going to be E. Okay, hopefully that makes sense. Let me erase this so I can reuse some of the steps. All right, next problem. A railroad track and road cross at right angles. An observer stands on the road 70 meters south of the crossing and watches an eastbound train traveling at 60 meters per second. At how many meters per second is the train moving away from the observer 4 seconds after it passes through the intersection? All right, so this is definitely the type of problem where we haven't done many, but drawing a picture is incredibly important here. Otherwise, I have no idea what I'm looking at. So let me try to draw this as best as I can, but bear with me. A railroad track and a road cross at right angles. Okay, so I'm going to draw my railroad track here. You can see I have these little stitches, though that's my railroad. Okay, and a road cross at right angles. So my road is going to be like this. That is not a right angle. Excellent. Okay, that's my road right there. And hopefully you can see how that might be a road. All right, road track and road cross at right angles. An observer stands on the road 70 meters south of the crossing. Okay, so the crossing's right here, 70 meters south. Let's say this person, I'm going to make this person red. He's standing 70 meters south. So he's standing right there. That is 70 meters south. All right, and watches an eastbound train. So east is this way, traveling at 60 meters per second. Okay, the train's traveling at 60 meters per second, but I don't know where to draw the train. Like, where do I draw it? So I'm going to keep reading. At how many meters per second is the train moving away from the observer 4 seconds after it passes through the intersection? Okay, so it's passing through this intersection 4 seconds later. So the train must be like over here. Train must be over there. So I'm gonna draw the train in, let's go with blue. The train's like over here. Right, so that's my train in blue because it passed through the intersection. Okay. Cool. And how fast is the train moving away from the observer 4 seconds after it passes through the intersection? Okay, so what I'm really trying to find is this distance. It's the distance between the observer and the train, right? That straight line there. I want to know how much that's increasing by, right? That's how fast the train's moving away. Okay, so my picture's roughly drawn. Let's label some things. All right. So what I know and don't know. So what do I know? All right, I know this is 70. So I'm going to label this as y. Y is equal to 70, right? Y is equal to 70. Cool. What else do I know? I know this something's 60 meters. All right, we have to give these variable names though, right? Watches an eastbound train traveling at 60 meters per second. Okay, so this train here is traveling at 60 meters per second. 60 meters per second. Well, what's that variable name? I'm going to give this train the x value here. I'm going to name it x, right? Which means if x is increasing at 60 meters per second, that means really what 60 is dx over dt. It's the rate of change of x. So this side of the triangle, dx over dt is equal to 60. Cool. How many meters per second is the train moving away from the observer 4 seconds after passing through the intersection? So I know t is equal to 4, right? T is equal to 4. What do I not know? Well, I don't know at how many meters per second is the train moving away from the observer. So I want to figure out how fast this green line is changing. I'm going to give this a totally different color altogether. I'm going to name this side Z. If I'm trying to find how fast Z is changing, that means I'm curious about dz over dt. I want to know how fast the straight line between the observer and the train, what's the rate of change of that? All right, I feel like that's as much as I can because I labeled all the values given in my problem. We'll come back to it if we need to. But step 3, let's identify an equation that relates all the variables. All right, here I'm relating 3 sides of a right triangle. It's got to be Pythagorean theorem, and it's got to be x squared plus y squared is equal to z squared, right? It's got to be that equation. So I'm going to implicitly derive this. So I'm going to take my equation, and I'm going to do d over dt for both sides. All right. So we did this once already, but the derivative of x squared, that's 2x. Then I have to multiply by dx over dt. Plus derivative of y squared, remember first I do it normally, so it's 2y. Then I have to multiply by dy over dt. And again, that is because this y and this t do not match. All right. Finally, this last side, derivative of z squared, that's 2z. And since t and z do not match, I have to multiply by dz over dt. Excellent. That's my step 4. Step 5, I plug in my known values and solve for what I don't know. So what do I know? Okay, so I don't know my x, but I know my dx over dt is 60. So cool. Do I know my y? I know my y is 70. That's nice. dy over dt. That is a good question, actually. Do I know my dy over dt? How fast is this side changing? Well, I said an observer stands there. It says the observer is not moving. So this side of the triangle y, the observer is not moving. So the rate of change of y is 0. dy over dt, if you think about it, is 0 because the person is just standing there. This side of the triangle stays 70. It does not move. So dy over dt is 0. So that's why it's useful to have my chart because I can go back and fill things out that I didn't think about. All right, 2z, I actually don't know z, right? At least right now. And dz over dt, that's what I'm looking for, right? So that is what I am looking for. Okay, so let's simplify this equation a little bit. Well, this is times 0, so it disappears. 2x times 60, so it's 120x, is equal to 2z dz over dt. So I actually need to know both my x and my z to figure out dz over dt, right? Which is what I'm looking for. All right, there's 2 unknowns. I need to figure out my x and z. Let's think about this. It's kind of tough. Well, what else have I not used? I know my t is equal to 4. Okay, I have not used that. Well, let's think about this. If my train is traveling at 60 meters per second, 60 meters per second, and I've traveled for 4 seconds, that means the side length x is going to be 60 times 4. Right? I've traveled for 60 meters per second, and when I do that for 4 seconds, that means I line up 4 of those 60 meters. So really, the x value of my triangle is 240, right? 60 times 4. Right, so I actually do know my x. My x is 240. All right. So x is equal to 240. And now my z becomes easier to solve. If I know y is 70, x is 240, I can use my Pythagorean theorem to solve for z, right? Because 70 squared plus 240 squared is equal to z squared, which means z is equal to the square root of this stuff. So z is equal to what? Z is equal to 250 according to this, 250. So actually also, because I figured out my x, I can figure out my z. Z is 250. All right, so I have all of the stuff I need now. Let's just figure it out. So it's 120 times 240, and I'm dividing it by 2 times 250. That's my dz over dt. So equals dz over dt. And you already saw from my calculator, this is definitely a calculator problem. It's equal to 57.6. That matches up with my answer choice A right here. Okay, hopefully that helps. All right, we're going to move on to this next section where I start dealing with more contextual applications of rates, but really we're dealing now with position, velocity, and acceleration. All right, so let's think about what the relationship is between these again. All right. So remember, here, I'm going to write this down actually. All right. Our position, velocity, acceleration. Well, what's the relationship between each? Going down the line, it's derivatives. If I were to go backwards, it is integrals. All right, so from position to velocity is a derivative, velocity acceleration is a derivative. When I go backwards, acceleration back to velocity is an integral, velocity back to position is another integral. All right, so hopefully that is helpful. Let's figure out what this is asking for here. All right, first question, the position of a particle is given as that function. Okay, so I'm gonna say position is this x of t function is equal to cosine of 3t minus sine of 4t. Find the acceleration at t equals 0. Okay, so I just need to do how many derivatives? Position to velocity acceleration, that's 2 derivatives. All right, so let's find first my velocity is my first derivative. Well, derivative of cosine of 3t. Notice first thing that I would notice here is a chain rule because I have a cosine outside function and an inside 3t function. So derivative of cosine is negative sine. I leave it inside the same, so 3t. Then I multiply by the derivative of the inside, so I multiply by 3. So really my derivative is going to be negative 3 sine of 3t minus the derivative of sine is cosine. I leave it inside the same, so 4t, I leave it the same. Then I multiply by the derivative of the inside. The derivative of 4t is 4. All right, so that's my velocity equation. Cool, I'm not done though, because I need to go one more derivative to find my acceleration equation. All right, acceleration of sine is cosine. Sorry, derivative of sine is cosine, so it's negative 3 cosine of 3t. But then I multiply by the derivative of the inside, so I multiply by 3 again, which changes this coefficient from negative 3 to negative 9. All right. Then minus 4 cosine of 4t. Derivative of cosine is negative sine, so that turns it into positive 4 sine of 4t. Derivative of 4t is 4, so I multiply by 4, which means I'm really going to multiply this sine of 4t. 4 times 4 is 16. All right, that is my acceleration equation. Now I'm going to find the acceleration at t equals 0. So I'm really taking this equation. I'm going to plug in 0. So I plug in 3 times 0, sine of 4 times 0. All right, let's keep going. -9, that's cosine of 0. Cosine of 0 is just 1. Plus 16 times sine of 0. Sine of 0 is 0. So it's 16 times 0. Well, that just simplifies to -9. So my answer choice is going to be A, -9. Okay, cool. Let's keep going. A particle moves along the x-axis with acceleration at any given time t, given as a of t is equal to 3t squared plus 4t plus 6. If the particle's initial velocity is 10 and its initial position is 2, what is the position function? All right, so let's think about this. Now we're going backwards, right? Because I'm starting with acceleration. So acceleration is given as 3t squared plus 4t plus 6. The particle's initial velocity is 10, its initial position is 2. What is the position function? So all I know, I'm starting with acceleration, I need to go back to position. So first I'm going to take the integral. So the first integral, to do one integral, I get my velocity. So I'm integrating 3t squared plus 4t plus 6. All right, so let's integrate that. That is a anti-power rule, so it's going to be 3t cubed divided by 3 plus 4t squared divided by 2 plus 6t, then don't forget plus c. All right, let me simplify this. So it's really t cubed plus 2t squared plus 6t plus c. All right, so I would keep going, but what do they say? The particle's initial velocity is 10. All right, so that means v of 0 should be equal to 10. So this whole thing, when I plug in 0, should be equal to 10. All right, so I plug in 0 for t, so 0 cubed plus 2 times 0 squared plus 6 times 0 plus c is equal to 10. Really, we actually jumped ahead here. We're doing the particular solutions solving for plus c, right? That's what we're doing here. Particular solutions solving for plus c. All right, that means c here is 10. C is equal to 10. So my velocity function is actually plus 10, right? Plus 10. All right, hopefully that makes sense. Cool. I'm almost at my position function, right? But I got to do one more integral. So to find my integral, my position function, I'm going to integrate this thing, my velocity function, integrating my velocity. Right, let's integrate that. So that's t to the 4th divided by 4 plus 2t cubed divided by 3 plus 6t squared divided by 2. This is all anti-power rule. Plus 10t plus c. And let's not forget the plus c. All right. Cool. There's not much I can simplify here. I guess 6 divided by 2 is 3. So 3t squared. Yeah, 3t squared. Okay. And I almost have my answer here, right? However, it could be A or B. Actually, it could not be A because there's no 10t. It could not be C, D, or E. Actually, based on this, my answer choice has to be B, right? However, if you might be like, how did they get 2 here? Remember, they told me my initial position is 2. That means when I plug in 0, which is my initial position, so this gives me my initial position, that means I plug in 0 for everything. So 0 to the 4th times 2 times 0 cubed plus 3 times 0 squared plus 10 times 0 plus c. This all still equals 2, which means my c must equal to 2. which means when I go back here, c equals 2. That matches up with my answer choice B. Okay. Next question. Choose the integral expression that would result in the total distance traveled on the interval from 0 to 3 if the velocity is given by the function v of t is equal to et minus 6. Okay, so here's the thing. Distance, this is related to position, but it's not exactly the same. But since it's related to position, I do know one thing. I need to integrate velocity, right? So I'm going to integrate velocity et minus 6 to get my position function, right? Position or distance, right? However, they say the total distance I travel from 0 to 3, that means I'm going from 0 to 3. I'm integrating specifically not to find my position function, but I actually am plugging in numbers into my definite integral to solve for the total distance. However, this is sort of a trap answer because you might think my answer choice is E. However, this is a trap answer because this solves for my total displacement, which is slightly different than total distance. And you might ask, what is the difference? Well, here's the difference between displacement and distance. So displacement, I'm going to write notes for here, and then distance, I'm going to write notes for here. All right, displacement is this. So let's say I travel 4 units this way, and I travel 4 units back. I actually end up right where I started, so my displacement is equal to 0, because I didn't technically move from the beginning to the end. I started and ended at the same spot. Distance would count all of that. So I move 4 this way, 4 back. That means the total distance I traveled is 8, which makes sense because I moved, right? I went 4 this way, 4 back. In total, I traveled 8. Even though I started off, I ended up at the same spot. Okay, so this travels for total displacement. Basically, displacement, it counts moving in the negative direction against you. Right here, displacement, notice when I started moving backwards in the negative direction, it actually started taking away from my displacement. I ended up back up at 0. Right, so what I want to do is take my integral and find total distance. Well, how do I find total distance? Well, I want to make everything positive. So I'm going to make my function e to the t minus 6 completely positive equals total distance. So how might I do that? Well, let's pull up my graphing calculator. This is a graphing calculator sort of problem. I'm going to plot my function. So e to the x minus 6. I'm going to graph this. And notice, here, I'll zoom in a little bit. This is my velocity function, right? So in this beginning part here, I'm moving. My velocity is not 0, right? My velocity is negative. So I'm moving, but I'm moving in the wrong direction. It's actually counting against what I calculate for my integral. So I want this all as positive. So what I'm going to do is figure out what's going on here, right? So I'm going to figure out this interval where it's negative. So I'm going to second trace here. This interval where it's negative. So left, right. I'm going to guess right here it stops being negative. So as 1.79175. That's the same as if I look at these answer choices, looks like it's ln of 6. Is that accurate? Yeah, 1.79175. Okay, so basically from 0 to ln of 6, I have negative velocity. So it's counting as negative distance. Counting as negative distance. And afterwards, from ln of 6 to 3, I'm cool. I'm counting as positive distance. All right, so let's actually clarify that. So when I integrate from 0 to ln of 6, this is counting as negative distance. So how do I make it not count as negative distance? Well, let's turn it negative, which actually turns this positive. Now it's counting as positive distance, which is good, because that is what I'm looking for. Positive distance. All right. My next integral, which was from ln of 6 to 3, that was always good. Ln of 6 to 3. This is already counting as positive distance. Okay, finally, I have both of these counting as positive distance. So I'm going to combine both these integrals. So really, I just split up my integral into two separate integrals and then made this one negative, so it actually turns positive, if that makes sense. So which one of these matches up with this? It looks like it's going to be answer choice C. C. All right, hopefully that makes sense. Cool, that one is sort of confusing though. It's a decent amount of work. Okay, if the position of an ant traveling along a horizontal path at time t is 3t squared, what is the ant's average velocity from t equals 1 to t equals 6? Okay, so average velocity, so I'm given position, I want to find the average velocity, which is basically the average rate of change. All right, so here's something I want to clarify. If I was given velocity, if I was given my velocity function and I want to find average velocity, I would do my one equation, which is 1 over b minus a times the integral from a to b of f of x or f of t dt. Right, that's my average value of a function equation. But that's because these are the same equation. I'm given velocity, and I want to find my average of that velocity, average of that equation. But since I'm given position, and I want to find average velocity, then I do my average rate of change formula. So that is going to be f of b minus f of a over b minus a. So it depends on the function that you're given, right? It makes sense. If I'm given my velocity function, then I just use my average value, the average value of that function, which is this equation. If I'm given a different function, I'm given my position, then to find a velocity, that's the same as finding the average rate of change, because velocity is the rate of change of position. So I'm going to use this equation, basically. F of b minus f of a over b minus a. All right, so that is basically from 6 to 1, so 6 minus 1. So that's f of 6 minus f of 1. So that's over 5. F of 6 is going to be 3 times 6 squared plus 1 minus 3 times 1 squared plus 1. That's equal to 21, it looks like. So my answer choice is D. All right, hopefully that makes sense. Cool. Now I'm going to move on to this first free response problem. And this actually continues a lot of the same concepts that we were just looking at. So first, the graph of the function given above is y equals v of t. So this is my velocity function, v of t. The velocity of an object moving on a line over the time interval from 0 to 8. At time t equals 0, the position of the object is 5. Okay, so that's actually sort of useful. If I were to write this, this is my position function. X of 0 is equal to 5. All right, first, when is the object at rest? By definition, at rest. Actually, I'm going to try to write all this out as much as I can. An object is at rest when v of t is equal to 0. So So when is my v of t here? I apologize for writing so horrendously. When is my velocity equal to 0? Well, it's equal to 0 at 5 and 8. So simple answer choices. The particle or the object is at rest at t equals 5 and 8. All right, evaluate the integral from 1 to 6. Explain the meaning of the result. Okay, let's think about that. If I'm evaluating the integral from 1 to 6, so I'm gonna actually highlight or shade in what that is. So that's this starting from 1 to 6. All right, first let's evaluate that integral. Remember, all this area is positive, everything above. This small little triangle here is actually negative. Okay, to evaluate this integral, what I would do is break it up into shapes. All right, so you can see what those shapes are. So first, let me just write this out. So let's see. First, I'm going to add this little rectangle here, which is base times height, plus there's a triangle up here, so that's 1/2 times base times height. That's the area of a triangle. Plus, there's a second triangle here. Hopefully you can see that right there. So it's another 1/2 times base times height. Then finally, this triangle right here is actually minus. I'm subtracting that triangle, right? So it's minus 1/2 base times height. All right. So a lot to write. I just wanted to have it down. Let me type it into my Desmos. Now let's just plug in my values. So first, this rectangle, the base is from 1 to 4, so it's 3. So times my height, which is 1. The triangle on top of it, so this triangle right here, that has a base of 3, a height of 1. Cool. This triangle right here is also positive, that has a base of 1 and a height of 1. All right, this triangle right here, I'm going to count that as negative, right, because it's below the x-axis. So that has a base of 1 and a height of 2. So evaluate this. Turns out this is equal to 4. All right. Now, we're asked to explain the meaning of this result. Well, remember, when I integrated my velocity, that is going to be my displacement from 1 to 6. And you might say, how do you know it's displacement? How do you know it's not your total distance? Well, remember, this is my integral. I counted this as negative. If it was distance, I would want to count it as positive. I would want to calculate for it up here as positive. The fact that I counted it as negative means I'm counting it against me. It's displacement. All right, so I would type that here. This integral evaluates the total displacement of my particle from t equals 1 to t equals 6. Okay, what is the position of my object at t equals 5? Well, I can calculate that by calculating for my displacement from 0 to 5. Right, when I calculate for my integral from 0 to 5, that's my displacement. That was similar to before, except I'm going to recalculate for my area. So you can calculate for this area yourself, but I'm going to get, let's see, 4 times 1 for the rectangle, plus the triangle on top is, again, 1/2 base of 3, height of 1, plus 1/2 base of 1, height of 1. All right, so what does that equal to? Let me write that here. All right, so the position of the object would be 6. However, remember the initial position of the object is 5. So it's actually 5 plus 6. So if I were to write this out, my equation to solve for this problem would have been my initial position, which was 5, plus my total displacement. So initial position plus total displacement is equal to my final position, right? Initial position plus whatever, however much I changed, that would tell me where I finally end up. So my equation is this, that equals 5 plus 6, that's equal to 11. Okay, next, D. Find the total distance traveled from 0 to 8. Okay, total distance, really similar. Remember, I'm taking my integral from 0 to 8 of my velocity function. However, this gets me displacement from 0 to 8. Remember, how do I get my distance? Well, to get my distance, I simply need to make everything positive. So I'm going to make this all absolute value. All right, so I go to my function. From 0 to 8, notice I have this negative part here. I'm going to make that all positive. I'm going to count for it as all positive. So actually, I could draw it up here like this as positive. Or I'm just going to label this. Remember, I'm going to count this as positive. So let's calculate for that. Well, I calculated for the part from 0 to 5 already. What did I say? It was 6, right? So it's 6. Then I'm going to calculate for this area right here. That is a trapezoid. Right, so I can calculate that as a trapezoid, or perhaps easier is calculate this as a 2 triangles plus a rectangle. All right, 6 plus 1/2 base height plus the second triangle 1/2 base height plus the inner rectangle. All right, 1/2 base height. Well, what is my base? My base is 1. My height is 2 plus 1/2 base height, so times 1. Times my height is 2. Plus my final rectangle has a base of 1 and a height of 2. Okay, so my total distance traveled when I count everything as positive is actually 10. All right, last part of this. At t equals 2, is the object speeding up or slowing down? Well, there's a simple way to remember this. It's speeding up. How do I know if something's speeding up? Because its velocity and acceleration will have the same sign. It can be positive, it can be or negative, but it has the same sign. If it's slowing down, velocity and acceleration will have different signs. All right, so let's calculate for this. At t equals 2, so what is v of 2 and what is a of 2? Well, v of 2, well, I just go to my function. This is my function v. At 2, right, my function's at like around 1.5. I know it's positive. That's all that matters. All right, a of 2. Well, you might be like, how do I find what is a of 2? I don't have a function a here. Well, remember, a is what? A is the derivative of velocity. So a is really v prime 2. How do I find v prime? I'm just going to go to 2 and I look at my slope. Well, what is my slope here? Well, my slope looks like my rise is 1. So rise is 1 divided by my change in x, or my run is 2. So it's 1/2. All right, so what are the signs? Well, my sign here is positive, and 1/2 has a positive sign as well. So both signs are positive. That means my function is speeding up, because when it's speeding up, v and t will have the same sign, so it's speeding up. All right, hopefully that makes sense, everyone, and it's helpful, and then you will answer these 2 free response questions at the end. Thank you, everyone. See ya.